morning. I will step right through. I thank Tom for a good introduction. And before I get into the material I have here, I want to first mention that when we transitioned from one program to another, and especially the shuttle program as it was, that we had budget constraints. That was a severe thing. We had to compromise, as was pointed out. And one of the things that was important was how much of the existing systems could we reuse. So as you all can tell, we reused the VAB, we reused the crawler, the crawler transporter, and the mobile launchers became reuse of the old launch umbilical tower platforms. And even the towers that were on those launch umbilical towers, 2 of those were removed and put on the pad. So that tower that sits at the pad was the same tower that was used in Apollo on the LUT. So we reused as much of this hardware as we could to cut down the front end or the development costs as possible. And I think it's important that that we make that known to you all and you realize that. I'm at a point in my life where I have to change my glasses frequently, and I'm right now at a point where when I look up here, it's pretty fuzzy. So I've got an appointment, but I'm a little bit lagging in getting my glasses changed. So I'm at my notes to see if I can't help that a little bit. The first thing when the program is accepted as and they accepted an architecture is to look and see now, are we going to be able to meet these requirements, and can you determine the functionality through verification to mitigate the risk of a catastrophic event? And that's pretty important. So when I look at those, first thing I look at is the fact on the Saturn I, we had a system that supported the vehicle that was totally active, and this system had to operate and release in order for it to be a good launch. If we had a failure of that system, it would have been a bad day. There was no backup. It was pure and simple a high-risk system. So likely we would want to try to avoid those kind of systems in the future. Same thing is true with the Apollo. We had multiple T0 swing arms. Well, they all worked really nice. However, you know, had one of them failed during the launch, I mean, it's a T0. That means you've already launched the vehicle, and if it fails, it's going to be a bad day because the vehicle's not going to tolerate running into one of those swing arms. So another design try to stay away from is T0 swing arms. One of the things that the early shuttle had was an external tank that was a lightweight balloon structure. In fact, it couldn't support the orbiter, and therefore the architecture had what they called a trolley, and this little trolley sat underneath the SSMEs under the orbiter and actually supported the orbiter weight to keep it from resting on the tank because the tank couldn't tolerate that. So the idea was that you would light the engines, and as soon as it built up thrust and carried the weight of the orbiter, this little trolley now would move off and get into a protective enclosure. However, if you had an abort and you shut those engines down before you launched, that little trolley had to get back up under there and receive that vehicle to support that weight in order to avoid a catastrophic event. One of the things, when I brought that to the attention of our program managers, they said, I think you're absolutely right. That's something we can't tolerate. And so immediately got with Jim Odom and Bob Thompson at JSC and discussed this and determined, you know, this was not a good architecture to start on, and we needed to change that. So that evolved into a freestanding external tank that could support that weight, and we eliminated that whole trolley system. Another item is a T0 damper arm. Again, if you have a very lightweight vehicle that's tall and slender, it's kind of like the CLV was planned to be, and it needed a damper arm to hold it. There again, if that needs to not be a T0 function, so it would be a bad day if it did not operate. At this point, I'd like to correct something that was said here about orbiter or crew abort systems. The original shuttle architecture had a crew abort system. This seems to be a lost identity here, but there was 2 solid rocket motors attached to the orbiter, one on each side of the fuselage. And that system was in the original architecture, and the program management deliberately removed those, because when you assess the probability of failure of those motors being on each side of the crew vehicle that close versus the solid motors you're trying to get away from, it didn't make a whole lot of sense. So as a result, they were removed. Needless to say, it took off a lot of weight as well, but and helped performance. But nevertheless, there was a crew abort system originally, and it was intentionally removed. One of the things that we needed to address, of course, was our natural environment. It's always a major function in designing flight and ground systems, is that you must be able to tolerate rain, wind, humidity, and et cetera. And one of the things that is also a function is the lightning. Apollo 12 was a case at point where the weather was looking pretty bad, but we really weren't in a storm or rain, and we launched Apollo 12. Well, unfortunately, it got struck by lightning. The Apollo crew capsule had circuit breakers, and however the launch vehicle did not. We were very fortunate. The lightning tripped the circuit breakers, so the system was total void of power for a period of time. And we had a very calm crew, obviously. They just simply reached down and reset the circuit breakers, and they had power. We were very fortunate. So another lesson is to make sure you don't launch one of these vehicles when there's imminent potential lightning in the area. Another one that, as Lewis said, this is kind of like being around fireside chat, and he told me this is storytelling, so I try to live up to his advertisement, you know, that I'm here to tell you stories. Well, one of the things that came late in the program and shuttle development was the concern about hail. And it was less than a year from launch time, and we had all this concern about, well, have we covered this? Have we covered that? Have we forgot anything? And they, oh my goodness, we don't have any hail protection. And being a part of the team that looked into those requirements, so I started investigating that, and I said, you know, we don't have any evidence of ever having hail at the launch area here, the Cape, or any place. Our meteorological station had no evidence of it. So yes, there's hail at Daytona Beach, there's hail south, it's everywhere, but this area just does not seem to ever get hailed. So I don't think that's a major risk. We ought to put that off. We don't need another delay in our schedule just trying to build hail protection. So the program accepted that, and it wasn't but a short time that I was visited by the media that wanted to talk to me about natural environments and how well it was affecting our shuttle program development. And so I expounded on the fact that this hail story, and he said, well, that was great. He was going to get a write-up and put in the paper about our natural environments. And anyway, shortly thereafter, I expected to see it in the paper, but it didn't show up. And I said, well, I breathed a sigh of relief. At least that's not going to show up in the paper somewhere in the back page or something. And anyway, lo and behold, on Labor Day weekend, here it is, front page, big article, expounding on the fact that I had assured him there'd be no hail. And I think you already understand where I'm going. It wasn't long after that we had a hailstorm. Well, guess what? The only place it hailed was at the pad. Really. Now that sounds spooky, but that's a fact. The only place it hailed was the pad. It didn't hail up at the VAB or anywhere else, just on the launch vehicle. And it did minor damage to the external tank foam and the orbiter tile, but nothing was major and serious to hold us up. But again, don't ever think you're in control of these things and you know it all, because there's someone else there that knows better. So it keeps you humble. Ice, frost, and debris. We could tell immediately that when we saw the architecture that we were going to be dealing with fragile tile, that we couldn't fly cryogenic vehicles with the way we had before, with lots of frost and ice on them. So we worked at that process deliberately and trying to come up with ground solutions, but they didn't appear to be anything practical whatsoever. So we eventually ended up with a compromise to insulate the external tank, and as best we could. And for those areas that we could not cover with an insulation, we used hot gas purge. So the nose cone has a hot gas purge. The inner tank has a hot gas purge to keep any from the exhaust of that gases from being below freezing. And the press lines that go up the side, they also purged with hot gas. So it was a combination of purges and insulation of the tank that allowed us to get a vehicle that we could fly for 30 years. Hazardous commodities. Of course, in this business, we deal with a lot of these, but there again, this is an area that we need to deliberately try to avoid as much as possible. Toxic fluids are a major concern. They drive costs. One of the things that is behind the scene that we have to do is all the people that could be exposed to hypergolic toxic fumes need to have health exams every 6 months so that you have a record in the event that any of these people get exposed. You know exactly what their exposure level was and how to treat them. So it's a very costly process, as well as the suits they have to wear and the team of people that maintain those suits. So that there again, we've been using these for years, but it's a very expensive process. Cryogenics, and the main concern in cryogenics is fire, water hammer, and the sensitivity to contamination and geysering. Geysering is probably a phenomenon that most of you probably are not very familiar with, but you are familiar, I'm sure, with a percolator coffee pot. Well, percolator coffee pot uses a geyser process to operate. The little bowl in the bottom is a heater, and you have a tube in there that has a capture bulb at the bottom that allows that water to boil and produce gas, and that steam now pushes the liquid in that tube up into the basket where the coffee grounds are to make the coffee. And if you notice when it percolates, you always hear this thump. That thump is a refilling of that system with water. That's the water hammer you're hearing. So now think about that in terms of something large like a cryogenic system with long vertical lines that are 50 to 100 feet long. You can get the same kind of situation. As you can see, if you had gas accumulated at the bottom of the line, as it rises, it's going to expand because the pressure is reduced and causes it to gasify, convert the liquid to gas, and you're going to produce a coalescent bubble, as we call it, and it will force all the liquid out of that line into the tank and leave it void. Well, that part could be a problem because when it spews into the tank, it can collapse the ullage and collapse the tank because of the drop in pressure. But the worst thing is that when you refill that line, that water hammer will destroy everything at the bottom. So you got to avoid geysers. So again, if you can avoid those kinds of designs, it's definitely recommended. This was an area that we undertook some changes in the tank because we built a thermal pumping loop on the tank to help us solve that initially, and finally evolved to understand that by using a helium boost system in there, we could operate that thing safely without the research system, and we're able to take that other line off. But again, it's a very difficult development area, and you need to be aware of it. Of course, contamination liquid oxygen is highly sensitive to any kind of hydrocarbon contamination, so any system that you use liquid oxygen or gaseous oxygen has to be surgically clean. Closed compartments. Closed compartments, again, are a difficult area. They drive costs. They drive costs because they require you to control that area. If there's hazardous gases that can be in there, you need to monitor those, so you have to have monitor systems. You need to put inert gases in there, but if you need to go back in those areas, you got to have a conversion system to get the inert gas out and air back in. You may not remember, but on the shuttle program, on STS-1, we were preparing and we went through an abort situation. Well, the guys were ready to go back into the aft compartment to perform work. They pulled off the door and made an entry, and the team did not have good clearance that system had changed over, and we lost 2 people in the back end of the orbiter from the nitrogen environment that was there. So again, closed compartments are very, very difficult to control because it's simply a control process in order to manage the safety working with those systems. We seem to have difficulty getting rid of those things. I don't quite understand that because the Russians fly open truss compartments, so I think we could learn from the Russians in that sense. Excessive free and trapped hydrogen. I think that it was mentioned ignition overpressure is a concern. We had a 6.4% model that was built in Huntsville to test these environments and to understand this overpressure, as well as to understand our acoustic environment, so we'd know how to design and what design to put in for acoustic suppression, or they call it sound suppression at the launch pad. We understood that there would be a lead hydrogen that would be expelled from that engine that would ignite once it became involved in the air, and it got its ignition from the engine ignition itself. So the question was, how much hydrogen would that be, and would it damage the heat shield? We convinced the people that sent us to run a test on the MPTA to try to understand that, and sure enough, the pressure levels were not going to be acceptable, so we were required to design a ground system that would burn off that hydrogen. You see all those sparklers, or they call them sparklers, at the bottom of the engines every time before the engines light. That's zirconium particles, 50 micron zirconium particles that are expelled from these little solid generators that blow them out across there like a little firecracker. And zirconium is pyrophoric, so it ignites in the air and burns and provides ignition sources for burning off that hydrogen, and it's worked very successful. The SRB, again, we didn't really understand the overpressure from SRB adequately, and STS-1, it was pointed out, we received damage on the shuttle from that overpressure. We weren't fully appreciative as exactly what caused that, but we determined that those sound waves that come from that are about in the 25 hertz range, and that I think the folks at JSC determined that the fact that this was 25 hertz and we needed about 1 foot of water to suppress it, that we could lace water across that opening, and that's what we do. We have a system that allows us to fill 1 foot of water over the entire SRB holes so that suppresses that ignition. Now, what we learned from this was that in trying to solve the problems of launching at Vandenberg with closed launch ducts out there, was that this SRB has a 51% excess fuel in the exhaust. 27% of the excess fuel is hydrogen. That exhaust comes out, you burn all the oxygen that was in the motor, so it's not burning when it comes out. However, as soon as it starts to entrain air in the boundary layer, you get already, you start getting oxygen available to cause this burning. Well, 5% oxygen is required to burn hydrogen, and therefore when you get this penetration of a mixing of 5%, you get ignition. It turns out that's about the midpoint in the mobile launcher itself when that happens, and so we get a detonation because that hydrogen level is at the lower end of the detonation level. So we actually have a hydrogen detonation inside the mobile launcher every launch from each one of those SRB holes, and that overpressure is suppressed by that 1 foot of water. As you can see there, the SRB exhaust hydrogen level is 2,743 pounds a second being exhausted, so it's a tremendous lot of hydrogen. We need to flow down the needs, goals, and objectives. That was one of our failures in the shuttle program, is that we didn't understand that well. We thought that, you know, if we had those, that we could take care of it, but I'm flowing those down into hard requirements and making it happen. It just doesn't happen. So all those, when you have needs, goals, and objectives, unless they're flowed down into hard requirements to force the designs, they just won't, they won't be visualized. The idea or the goals on the shuttle program was a 160-hour turnaround, which is essentially 2 weeks. We had a 24-hour notice to launch from rollout of the VAB, and then it was added that it would also accommodate a rescue, which means you had to be able to change out payload at the pad in a 2-hour countdown. And the assumption was that if we did all that and we flew 40 launches a year at Kennedy, that we could achieve about $100 to $300 a pound to orbit, which was going to be very economical. The results of focusing on performance and not have flown down those needs, goals, and objectives can be seen here, that the 160-hour turnaround turned out to be a 126-day standard template. That's a 9-to-1 ratio. And 24-hour notice to launch turned out to be 26 days. That's a 26-to-1. The difficulty there was front-end money again. We needed another $4 or $5 million to put in a new LOX transfer line that allowed us to increase the LOX flow rate, and we would have needed to automate the crew ingress system, which would have been changes to the orbiter, and the program just didn't have the money, and so we didn't accommodate it. So our 2-hour countdown turns out to be 8 to 9 hours. Now, we typically design for good reliability, and probably our pedigree comes from building airplanes there and using the same kind of logic. However, the application of space is a lot more severe than airplanes. No one flies airplanes continuously for 7 days or 30 days. And what we find is that because of the complexity of these vehicles and so much hardware, that about 40% of our processing time in the OPF is due to change out of or repairing problems and changing out of failed hardware. It's not to say we got poor hardware, it's just that there's so much that the probability drives you to have that kind of a failure count. In the future, we ought to be designing for maintainability, which would drive those requirements higher on the reliability side and achieve better life, because it's that function alone causes a loss of productivity of that orbiter. Instead of that orbiter achieving a 10 flight a year, we only achieved about 2.5 flights a year at our maximum capability, and this is all because of the complexity of the system as well as the repairs that are necessary. There's just a matter of interest, there's 102 interfaces on the flight vehicle that require ground servicing for every launch. So you see the complexity I'm talking about. Of this, there's 54 fluids in the program that has to be managed through a procurement process, and we need to know in detail the commodity purity and characteristics. So it requires all these things to be tested and verified and maintain the cleanliness of these systems. Of that 54 fluids, 27 separate fluids are serviced in this vehicle every flight. So it's a huge amount of servicing is required. And again, we got to concentrate on better integration of these functions so we have less interfaces, less fluids to service, and that's the only way we're going to really achieve higher affordability. Our resultant flight rate, as you can see, was 7 to 8, and actually it's down more like 4 or 5 these days. So the program labor increase, and I'm talking program, not just KSE, is about a 21 per flight. So it's a very labor intensive the way we ended up. So this is something we can learn from the process. I'm not shuttle bashing, believe me. I think the shuttle is one of the greatest vehicles, well, it is the greatest vehicle that the world has ever seen fly in space. But we've got to learn from what we've done and do better to achieve affordability in a sustainable system. The cost per pound, of course, is 30 to 1 factor. Instead of bringing the cost down like we had planned to 1 to 300, it's much higher. And again, we did achieve cost reduction. This is something that's not very much told, but we did achieve a cost reduction of about 3 to 1 over the expendable process during Apollo. So I do believe that we must maintain our focus on reusable systems if we ever plan to achieve high affordability. The message here is the design trades that we do are focused on the lowest subsystem, and we teach our people this, by the way. If you take courses, and I'm not sure about APPEL, but I think we're still teaching people to actually optimize around the lowest subsystem, and this will achieve you the greatest performance. And this is something that we need to change, because we need to not only do that, but then as a last step, verify that the overall system has been optimized. That's the part that we miss, is overall optimization of the system. We would change many of these if we were to do that and not end up with the systems that we have, if we are focusing on life cycle costs, of course. I wanted to mention here that as an example of complexity here, the SSME is a fantastic rocket engine, but that engine requires 28 vehicle support systems to satisfy it. That's a huge number of subsystems to try to support that element. And again, we need to look at ways to decrease that. And that's one of the measurements we use to measure different propulsion systems. We evaluate one system or another. That's one of the characteristics we use to help evaluate that. The orbiter hydraulic system is a distributed hydraulic system. And one of the choices in that, because we didn't want to fly the weight of hydraulic fluid in a line that run from the system to the mow line, requires us to go in and break the integrity of that system every time we fly. We have to go in with a ground system in order to operate the landing gear. So you can't leave that system intact. Again, that requires additional servicing and additional hardware. And I'd like to point out that in 1960, we had a system called the purging system that started with a distributed hydraulic system. We went to unitized components that eliminated that distributed system, and we reduced our mechanical manpower at the launch pad by 50%. So the hydraulic systems are very, very labor intensive to maintain and operate. The idea behind a component system, even though it was still hydraulics, was that if it failed, we could remove that component, take it to the lab, and work on it in the lab, and get it offline, so it wouldn't hold us up. That was a real novel design. It was only held together with one bolt and a simple electrical connector. So it was very easy to change and very quick. And the hydraulic system, as we have it in shuttle, requires about 50% of the electrical power just to keep the fluid warm, so the system will be functional when you return to Earth. So again, another reason why to avoid distributed hydraulic systems. The SRB TVC has a distributed hydraulic system that's powered with a hydrazine system, very similar to the ones that are in the orbiter. And we've made several attempts to try to get that simplified, but again, it's we've frozen the design, as Tom says. So, but the next systems ought to avoid these complex designs. Unfortunately, we hadn't accomplished that on Constellation. To my demise, we've seen the result of that. Unless we get the cost down and get affordability and sustainability, we're not likely to proceed. So we need to get it right. I see the time's up, so I'm going to jump over to the last slide, and you'll get my materials, I assume, so you can read these over and gain from it. But I want to leave you with the bang at the bottom there. System design must be accountable for controlling the life cycle costs, including its downtime. We must change the way we design our design process, and if we want affordability, that we've got to take these things into account and have a cost control system in place. We suggested it be something like the way we control weight. I know that's going to require manpower, but you either pay me now or pay me later. So I advise that we have cost control systems put in place to help us manage the cost drivers that go into these designs, flight and ground, such that we can achieve affordability. Thank you.